Welcome, everyone. My name's Tim Elam, and welcome to Buena Vista Museum's Meet the Expert event. Today, we're fortunate to have a wonderful speaker, Matt Herman, Dr. Matt Herman from Cal State University, Bakersfield. Matt will be speaking to us about earthquakes in Kern County and beyond. As we all know, earthquakes are something we live with in Kern County, those of you from Kern County anyway. Our last large earthquake in the San Joaquin Valley, at least the Southern Valley, was in 1952, but much damage resulted from a relatively recent earthquake in the California desert, the 2019 earthquake near Ridgecrest in the Eastern California desert. Dr. Herman is a geologist who researches earthquakes and will present basic information about how geological processes in the earth can cause earthquakes, and whether some earthquakes can cause other earthquakes to happen. He will discuss where the largest earthquakes tend to occur around the world and discuss earthquake risks here in Kern County. Dr. Herman is currently assistant professor of geology at Cal State University, Bakersfield. He received his bachelor's degree in geology and physics from Amherst College in Massachusetts, and his master's and PhD degrees in geosciences from Pennsylvania State University. While at Penn State, he was funded by NASA to use satellite observations to study the very largest earthquakes in the world. After Penn State, Matt worked as a postdoctoral student at Utrecht University in the Netherlands before starting his work at CSUB about a year ago. While in the Netherlands, he worked on developing sophisticated computer models of earthquake processes. He says that when people seem surprised that he studied earthquakes in a seismically inactive place like the Netherlands, he would always tell them that's the best place to work on earthquakes is from afar. I feel like Matt and I have a somewhat similar academic experiences, starting with coursework in the physical sciences such as chemistry and physics. Being the slow learner that I am, it took 4 years for me to figure out that geology was going to be my future. Not so with Matt. He figured it out a lot quicker. In reading Matt's bio, he's something of a Renaissance man, seems to me. He grew up in the Midwest in St. Louis and was interested in all things science, math, and technology. He says I was a real nerd, but he also played football, basketball, and baseball in high school. He is truly as excited about science today as he was when a kid. That's great to hear and something many of us can relate to. The year after he started his PhD at Penn State, he met his eventual wife. They settled in Bakersfield about a year ago, and their soon-to-be one-year-old daughter is learning everything about science. One of his daughter's favorite toys is a computer keyboard. That I cannot relate to. So one more statement here. This time of year is the time of the annual Great California Shakeout, an earthquake preparedness event open to everyone. The Shakeout Day will be October 21st. You may have heard of this event. It's been going on for about 15 years. Go to www.shakeout.org to find out more about earthquake preparedness. Now, before we get started, and I'm just about to the end here, I'd like to let you know that if you like today's event and you'd like to see more content of like this from Buena Vista Museum, I invite you to make a donation. You can make that donation to the museum anytime at buenavistamuseum.org/donate. Also, if you would be so kind as to keep sure your devices are muted. If you have any questions during the presentation, please type them in the chat window. There should be a chat button on your screen, and I will monitor that. I'll look at those questions as we proceed. The presentation will likely be about 40 minutes, so there'll be plenty of time for Dr. Herman to address your questions. Without further ado, as they say, I'd like to go ahead and welcome Dr. Matt Herman.
Thanks, Tim, for that great introduction. And yeah, I will actually be talking about some of the things Tim mentioned, some of those earthquakes, great shakeout, things like that. So let's get into it. As Tim said, I'm an assistant professor at CSUB, and I study earthquakes. And when we talk about, okay, let me click on that. Here we go. When we talk about geologists and seismologists and all of these people, studying the earth, we say geologists study rocks. We say seismologists study earthquakes and faults. We say, geochemists study the atoms and things in minerals. But the reality is a lot of us are just really good at making maps. So we're going to start with a map. And here we are, sitting in Bakersfield, and it's right here. You can see the San Joaquin Valley down here. You can see the Sierras. You can see the desert to our east. To our west and to our south are the coastal and transverse ranges. And of course, the big city to the south on the other side of the transverse range is Los Angeles. So in all of these maps, as I continue to show them and put some different things on them so we can think about them, just remember, at least I am sitting here in Bakersfield. Many of us are sitting here in Bakersfield, but that box will always be there for you to know, kind of orient yourself where we're sitting. We're down here in the southern end of the San Joaquin Valley. Okay, so let's start adding to our map. Let's start thinking about the features that are in Southern California, the earthquakes and things like that. The first thing I'm going to add to the map is the San Andreas Fault. Okay, so why the San Andreas Fault? This is a major fault. It runs along the western side of the valley, along basically the whole length of California, from north to south along its western side. And this is a globally recognized sort of iconic fault. Now, why is it so famous? Well, first of all, it has big earthquakes on it. I think everybody probably in this talk knows the San Andreas Fault is known for having big earthquakes on it. For geologists, but also for other people, it's iconic because you can go to it. You can put your finger on a plate boundary. You can put your finger on the fault. You can see it in a lot of places. That's really cool because you can't always see these things. But probably most people, if you're a non-scientist, know about the San Andreas because of the movie with Dwayne "The Rock" Johnson. This came out a few years ago, and you can see him giving his smoldering look from his helicopter as LA and San Francisco are collapse from giant earthquakes shown in Hollywood behind him. So this is, how Hollywood thinks about the San Andreas. But what about real earthquakes? What really happens in California? What are the dangers they pose to Bakersfield, to LA, to other places around here? So let's add some real earthquakes to this map and think about where they happen. Okay, so on this map, every single circle on here represents an earthquake. The small circles are small earthquakes. The big circles are big earthquakes. And we'll talk a little bit about what that actually means, but I put everything magnitude 2 and larger in California since 1990 on this. And there have been 67,000 earthquakes in this map frame since 1990. That's a lot of earthquakes. Now, most of these are small. Most of these are 2s and 3s, and people barely feel them, if at all. But even these small earthquakes are starting to show us something about California. First of all, let's look at the San Andreas, right? So up here in the northwest end of the San Andreas, we see this line of earthquakes right along the fault. Okay, so it's like, oh yeah, this is a seismically active fault. But then there's this section of the San Andreas, kind of through most of the middle of our map here, it's still red. There's like no earthquakes on it. So what's the deal there? What's actually happening? And in fact, if you notice, there's a lot of seismicity. Most of these events are actually happening off the San Andreas, right? There's white circles all over the map that are not on our big San Andreas fault, okay? They're forming these lines over here to our east, some in the Sierras. We see some in the valley. We've got these in the desert. We've got these down near LA. So tons of earthquakes, but yet our San Andreas Fault is not necessarily hosting most of them. And so some of these have been quite large, both recently and over the more distant past. So let's think about some of the most significant earthquakes that have happened in this region. I'm going to take you way, way back. I don't think anybody in this talk was alive in 1857 when this earthquake happened. If you did, you should go to the Guinness Book of World Records and submit your age. But 1857, the Fort Tejon earthquake. This is so old, we didn't have seismic instruments back then. So all we can do is use historical records, written records, and evidence of damage to try and figure out how big this earthquake was. This earthquake happened at the orange star up here, and we think it was about a magnitude 7.9-ish, right? I mean, there's wiggle room. We didn't have detailed observations to tell us how big it was. So what does a 7.9 do? You know, people were still living here, and so there were newspapers. The Santa Barbara Gazette back in 1857 interviewed people who had been in this earthquake. So Mr. Warner arrived here on the 17th from Fort Tejon, okay? So he's coming from down here near the earthquake, and reported that all the houses, with 2 exceptions, were thrown down or otherwise injured so as to be rendered entirely useless. Huge damage. The shock was preceded with a peculiar rushing or rumbling noise, and for more than a week thereafter, noises somewhat resembling distant thunder were heard, right? This sounds apocalyptic. The damages are estimated at $50,000. Well, $50,000 in today's dollars isn't too much, but back then it was $1.5 million, you know, if you adjust for inflation. So, okay, that's still not that much, but you got to remember Fort Tejon wasn't exactly a populated city, right? This is extreme damage to just a small fort. What about closer to here in Bakersfield, the Kern River Valley? You know, the Kern River runs right through Bakersfield. 2 companies of US troops were having their horses herded in the Kern River Valley. Upon looking at the river, they were astonished to see the Kern River running upstream. This earthquake caused the river to go the wrong direction. Large trees were uprooted, and in the language of some who were there, all creation seemed to be going in one eternal smash. Again, apocalyptic language to describe what happened here. The water in Tulare Lake was upheaved to an unknown height, and large quantities of fish were thrown upon its banks, where they have remained. And this is really biblical. You know, this is an extreme event with extreme consequences. But it's a long time ago, so we don't know in detail what happened. We have to make our best guesses based on what we know today. So let's fast forward a little bit to something a little more recent. Tim already mentioned our last really big local earthquake was in 1952, the Kern County earthquake, also known as the White Wolf earthquake. And we had modern seismic instruments back then and people who understood how the earth worked pretty well, but this earthquake has actually stumped a lot of really, really good scientists. Tim and I were talking about this event right before this, this presentation. And estimates of the magnitude range from 7.3 to 7.7. I mean, this is a big range, right? Shouldn't we know what's going on if we have modern instrumentation? No, this event is still got a lot of questions associated with it. But it's the best guess right now is somewhere around magnitude 7.5. Well, what did this earthquake do? Again, newspapers tell us a lot about the damage it caused. Quakes, shocks, Rock County. Kern suffers more damage on the 3rd day because of aftershocks. Much of Arvin, downtown area, to be condemned, right? Lots of damage to the extent that you can't live in or work in these buildings anymore. Here's downtown Bakersfield. Some of the articles I read about this said it was a natural total renovation. You know, these buildings had to be taken down and they had to rebuild a lot of downtown Bakersfield. Tehachapi, just east of here, got it even worse. So you see Bakersfield, some of the buildings got a lot of damage to them. Tehachapi, a lot of the buildings fell over. They totally collapsed. So Tehachapi got shaken even harder than Bakersfield. Okay. Fast forward again, this might be an earthquake that some of us here remember. 1992, out east in the desert. Magnitude 7.3 earthquake over here where the star occurred. Now, this didn't shake Bakersfield or Kern County too hard, but if you were standing there, you know, Big Bear Lake, your building got destroyed, right? This is, again, really extensive damage local to the earthquake. 2 years later, magnitude 6.7. This is the smallest earthquake that I've talked about so far, but look at where it happened, right? This is in the northern part of LA. So there's a lot of people live here. And it did damage to the local Cal State campus, CSU Northridge, toppled Interstate 5 connector, right? Extensive damage, was very deadly. Okay, and then Tim already mentioned our last actually big earthquake may not be the 1952, it may in fact be the 2019 Ridgecrest earthquake. And there were 2 of them 2 years ago in July 4th. You know, people might have been out partying. There was a smaller earthquake and people may remember that. Well, the big one happened 2 days later, magnitude 7.1. And again, in Bakersfield, this wasn't too damaging, but if you went nearby into Trona, you know, your house was destroyed. The Kern County Library, the Ridgecrest branch, you know, somebody's got to put all these books back, right? The shaking knocked all the books out of the shelves. So although the damage from this event wasn't widespread, locally, there were pretty severe consequences. So we've looked at these few different earthquakes with different magnitudes and different sort of damage or descriptions of damage. So over the past century and a half, Southern California has been shaken pretty hard a few times. Now, you know, the magnitudes of these range, right? You know, we've seen on this map, there's everything from 2s to almost 8s. And we want to think a little bit more deeply about these events and where do they occur? What are their impacts? How do they even happen? And maybe if we can do a better job of understanding the science behind them and understand sort of the complex and varied behavior of earthquakes here, we can understand earthquakes in the rest of the world, and vice versa. If we can understand earthquakes in the rest of the world, we can do a better job of minimizing hazards and minimizing the risk here in California. Okay, so we want to answer a couple of just basic questions. First of all, what is an earthquake? I've been talking about these things like everybody knows what an earthquake is, but you know, let's have a refresher. 2, again, I've been talking about this thing magnitude, like everybody knows what magnitude is. And maybe everybody has some idea of what magnitude is, but again, let's think about what it actually means. And finally, you know, this is the main question. Are these the biggest events we can expect here in California? And how much does size really even matter? So we want to start asking and answering these questions in order to say, you know, get ourselves prepared for potentially large shaking and destructive effects of earthquakes. So let's start. What is an earthquake? This here is a picture of the Carrizo Plain. It's about an hour west of Bakersfield by drive. And this is a great place to start thinking about what an earthquake is. An earthquake is just a sudden release of energy that occurs by slip on a fault. Okay, so some of these words people may know, sudden release of energy. Okay, that we can kind of think about what that means. Slip and fault, those are geology words. So that might not be something everybody's familiar with. Well, what's a fault? A fault is just a crack or a fracture, a break in the ground. And this here, the Carrizo Plain, is an iconic image of a fault. And in fact, it's our fault. It's the San Andreas Fault. Okay, so if you drive out west of Bakersfield, you can go touch the San Andreas Fault. You can see it really clearly. Okay, so this fault, we know it has big earthquakes. Why does it have big earthquakes? If this fault were just sitting here with nothing happened to it, we wouldn't be worried, right? It would just be, okay, there's a break in the ground, something broken, we're done. But that's not what happens. It turns out the 2 sides of the fault are moving past each other. And they're moving very slowly, but inexorably. These are tectonic plates, right? These are the size of continents that can't be stopped. So they're slow, but you just can't stop them. And they move at about 40 millimeters a year. 40 millimeters, about 1.5 inches. So you can pull out your ruler, you know, got your inches on here. You may not be able to see me, but you know, 1.5 inches is about, I don't know, half the length of my pointer finger. It's not very far. But imagine doing this over 100 years, 200 years. Then we're getting several feet, right? We're getting pretty far. And the thing is, during that time, the fault is stuck. It's like it's Velcroed together. So the 2 sides are moving past each other, and this fault is stuck. So the rocks, they're actually kind of like springs or rubber bands. And as they move, they're building up, they're stretching, they're deforming and building up until finally the fault is not stuck anymore. that fault breaks. And when it breaks, pop, everything moves and we get an earthquake, okay? So what does this look like in sort of a cartoon image? We see here the two sides moving past each other. They're stuck at the fault. Between them, the faults bend and bend and bend until finally they slip and they snap by each other. And this happens again and again and again. It takes hundreds of years of motion to build up enough stress, enough force to break the fault. But when it does, it happens in a minute. And so you have hundreds and hundreds of years of energy, boom, gone in a minute. That's why these earthquakes are so destructive, the sudden release of energy. Okay, so here is our Carrizo Plain. Let's zoom back out a little bit to our map here and look at Bakersfield. And this is just our little corner of the world, right? It's got a lot of earthquakes. It's got a lot of damaging earthquakes, even some big ones like Fort Tejon and White Wolf, right? But we see the San Andreas. It goes off the northwest corner of the map, this red line, and down in the south corner, the southeast corner, it goes off in that end. So is this all that we need to worry about? Or, you know, maybe earthquakes happen around the rest of the world and we can learn something from them. So we're going to take a global view. We're going to zoom out a little bit. So as we zoom out, you know, we're sitting here in California. Again, I put Bakersfield. It's obviously much bigger on the global view now that we're zoomed out, but I wanted you to be able to see where Bakersfield was. And these red lines here represent other major faults. They're like the San Andreas in some ways, major fractures in the earth. But, you know, we see them going all around the earth. We see them going up to the north. This is the San Andreas continuing. And then there's another fault that goes past Northern California and Oregon and Washington and over here to Alaska. And then we see down here, it goes down next to Central America and Mexico, down here, South America. So these major faults all over the place, these major fractures. Okay, so, you know, let's put some earthquakes on this. Let's see where big earthquakes actually happen. Presumably, California's got a lot of earthquakes, got a lot of big earthquakes. California's going to light up, right? Well, that doesn't seem to be the case, okay? We do see some big circles on here. I've put magnitude 7 and larger earthquakes since 1900. That's more than 100 years of earthquakes. We see a little dot here. We see a couple little dots down here. But California, I didn't ignore it. I plotted all the earthquakes on there. California's earthquakes are puny compared to the rest of the world. Okay, they're so small, you can barely even see them unless you have a high definition screen, you know, but let's look at some other places. Up here in Alaska, look at these giant circles, you know, along the whole red line here of the Alaska and the Aleutian Islands. Those are some really big earthquakes. Look down here in South America, particularly in Chile, which is the southern part of South America here. This circle's enormous, right? That's the biggest earthquake ever recorded. Okay, but that's not the only one. There's lots and lots of big earthquakes that have happened in Chile. So, you know, Mexico and Central America have a lot of earthquakes. We'll talk about an earthquake in Japan later as well. I mean, California, just from a global perspective, is kind of nothing. So what's the deal here? What determines how big an earthquake can actually be? We're going to do a thought experiment. We're going to start our thought experiment like all good thought experiments should start, at the library. Okay, so here is the CSUB library. If you haven't been here, well, the library is like a great place to go if you need to do background research on anything, if you need to find something to read, fictional or non-fictional, talk to your librarians. They are experts at helping you find things. You know, the library is like the place to go. But today we're actually going to destroy the library. Okay, so how are we going to destroy the library? We are going to put an earthquake on this picture. So we're going to imagine that there's an earthquake occurring on a small fault on the sidewalk. This earthquake's going to be about 6 feet long. Okay, so you can imagine if the two sides of this small fault move past each other, the earthquake would be small. Indeed, you know, if you were standing right here on the sidewalk, you'd be a little irritated, right? If that moved, you might be knocked to your knees or something. But if you're standing over here in the grass somewhere, up at the library, or even where this picture is taken, we wouldn't even notice it, right? right? We break the ground by this much all the time when we're doing construction projects. So this isn't a very big earthquake, right? We can make it bigger. Let's make it bigger. Okay, so we're going to zoom out a little bit. So now we're looking at CSUB campus. This is an image taken from the air, beautiful sunset, sunrise. I actually don't even know off the top of my head. It looks like a sunrise. But anyways, we're going to imagine now that instead of just breaking a part of the sidewalk near the library, we're actually going to break the ground all the way across campus. So now the fault, instead of being a few feet long, it's going to be 3,000 feet long. It's going to cross all of campus. Well, now if this fault broke, this would be damaging to all of campus, right? If you're standing on the near side here, maybe you're standing, or far side, what if you're in Science 2, where my office is, right? And all of a sudden, this side of the fault lurches, right? Because the whole ground is moving during the earthquake, right? You would notice that, right? That would be a significant event. But if you're standing in downtown Bakersfield, or certainly if you're in a city outside of Bakersfield, you might notice the shaking, but it wouldn't be too intense. So a fault this big is about a magnitude 4 earthquake. If it's right under you, you notice it. But if it's not right under you, it's not too concerning. But we can go bigger. Let's do that now. Okay, so zooming out again. Now we see Bakersfield here. It's sitting in the valley. We see the Sierras over here on the right side. We see the Kern River coming out of it. Okay, so campus sits over here, kind of in the bottom left of our image. Now we're going to break a fault the size of Bakersfield. So instead of a couple thousand feet long, we're going to 8 miles long. And if we do that, we're starting to get a pretty significant earthquake here. So our earthquake now, is going to be damaging to all of Bakersfield, right? If the upper side of this fault starts moving suddenly, right, that's moving all of Bakersfield. And we're damaging all of Bakersfield. But if we're, in LA on the other side of the transverse range, if we're, up the valley somewhere in like Fresno or even further in Sacramento or San Francisco, we might feel a little shaking, but it doesn't bug us too much. But here in Bakersfield and the surrounding regions, this is pretty significant. In fact, a fault of this size, we're getting bigger. We're now at a magnitude 6.5 earthquake. Okay, but we can go bigger. Okay, so now I've zoomed back out to our map of the Southern Valley and our Sierras and everything. Now we're going to break the entire southern San Andreas Fault. So we're going to start up here at the Orange Star, and we're going to break the San Andreas all the way down here past LA. So as far as we can tell, this is actually the scenario of the 1857 earthquake. This was a magnitude 7.9 earthquake. And in fact, it's a little hard to see in here, but if you remember, this is the section of the fault that had no seismicity on it when we looked at it. Well, why does it have no seismicity? It's because it's stuck. It's because it's stuck, and it's been stuck since 1857, building towards the next earthquake. Okay, so this region, is a major seismic hazard from the San Andreas Fault, in addition to all these other little earthquakes. In any case, the 1857 earthquake broke 200 miles of the San Andreas Fault. This is now a big earthquake, right? But this is about it. This is about as big as California earthquakes can get. We can't go too much further south. The San Andreas doesn't go that far south. We could go north. The San Andreas does go further north, but there's a couple of problems. First of all, there's this region up here, a little further north, where the San Andreas doesn't appear to be able to have earthquakes. And so we can't connect this earthquake to the ones up north. But the northern part can also have its own big magnitude 8 earthquakes too. And in fact, we do this exercise in my class. We do the exercise where we say, what if we did break the whole San Andreas Fault? And you can get something like an 8.2 or an 8.3, but still we're not talking these really, really big earthquakes that we saw on the map. So this is pretty puny, remember, by global standards. This earthquake is the size of this tiny little dot here. You may not even be able to see it. So a magnitude 8 earthquake barely registers on the globe. But we do see some big earthquakes happening elsewhere. Alaska, Chile, Japan, Indonesia, places like that. So what's the difference between California and these other places? And to answer that question, we have to look down. I mean, literally, we are going to look down into the ground under our feet. And we're going to see how these faults behave in the earth. So we imagine we could cut a slice across from west to east here, like the earth was a sheet cake, and we're going to take it out and look at the fault down underground from San Luis Obispo across Bakersfield into the Mojave Desert. Okay, so we cut out our slice. What do we see? Okay, the San Andreas Fault goes vertically down into the ground. And so over here, we've got the side, to the west of the fault. Over here, we've got the side to the east of the fault. Okay. Now, what I want to put on here is a representation of the temperature in the earth. So as we go down in the earth actually heats up. Sitting here in Bakersfield, we're in a 100-degree day. And okay, 100 degrees feels really hot. But the earth gets much hotter than that as we go down into it. So at the surface, we're actually relatively cool. But as we go down in the earth, we get hotter. What does that, well, okay, we get hotter, fine. What does that mean for earthquakes? It turns out there's a depth down in the earth at which it's simply too hot for earthquakes. That's about 600 degrees Fahrenheit. And there are some technical, geological, geodynamic reasons why this is the case. I'm not going to go into them in great detail here. But all that matters is below this depth, we can't have earthquakes. They just don't happen. We can look at all the earthquakes that have ever happened in California, and they're like none deeper than this level. But there are lots of earthquakes shallower than this. We have them all the time. So practically speaking, what that means is that the San Andreas Fault can only break from the surface down about 10 or 15 miles. Okay, once we get 10 or 15 miles down, it's just too hot. We can't have any earthquakes anymore. Okay, so that's our limit. That's the biggest we can break on that crack, on that fracture. Okay, but what about other places? What about Alaska? What about Chile? What's going on there? So I have taken you up to the North Pacific Ocean. We've taken a big trip here. Okay, so we've got Alaska up here. Here's the Aleutian Islands. This is the Pacific Ocean. And the Pacific Ocean actually sinks northward underneath Alaska and the Aleutian Islands. It does this slowly, at a very similar rate as the San Andreas moves, but it does it, again, inexorably. It's hard to stop the whole Pacific Ocean from doing this. We call this in geology something called a subduction zone. And subduction zones are just fascinating. There is so much interesting, mysterious stuff going on there. First of all, it's intense earthquake activity. Those are where the big events happen. The second largest earthquake ever recorded was up here in Alaska. Okay, 1964, giant earthquake, huge tsunami, killed people in Hawaii, thousands of miles away. But on top of this, it's not the only problem, right? All these triangles here are volcanoes. Subduction zones have these explosive volcanoes. This is Redoubt back in 1990. These are explosive, dangerous volcanoes along the entire length of these subduction zones. And almost all subduction zones have these. Okay, and then on top of it is the deepest part of the oceans. You see this dark area here. These are the trenches. These are hard to explore because they're so deep. The pressure is crushing. It's hard to get down there and explore. But we've sent unmanned submersibles down there, and we see very strange life that is adapted to dark, cold, crushing pressures. Okay, so these subduction zones are, as I said, really mysterious places, but we're going to focus on the earthquake aspects of them. So I'm going to draw another slice across our subduction zone. And when we do that, we can draw a cartoon image here. Okay, remember the Pacific Ocean, it's moving northward, and then it sinks, it dives underneath Alaska here. So we've got Alaska over here, it's sitting on the surface, but the Pacific Ocean is coming over here, and it then goes down underneath Alaska. Okay, so what's actually going on? This is a quick video, a piece of a video from one I made back when I was in the Netherlands about subduction zone earthquakes. I'm not going to play the whole thing, and I'm hopefully going to keep it on mute while it's playing. Yep. So here's what's happening. The Pacific Ocean is slowly going down. The two plates are locked. Remember, they're stuck together like Velcro. So as the Pacific plate goes down, Alaska is bent like a diving board. You can see it's getting redder and redder, and more stress is building up. Now this clock up here is going to tell us when the earthquake is. It's going to happen at noon. Okay, so it's going down, and finally we're getting really close. Oh, there's too much stress, they're gonna break. And it breaks and it bounces back, and they have a huge earthquake. And these earthquakes are underwater. So they move the water column, they cause a tsunami, right? And these tsunamis can be way worse even than the shaking itself. They hit the local areas like Alaska, but they also cross the ocean, and they could do damage across the ocean. And in fact, this was the devastating part of the 2011 Japan earthquake. It wasn't the earthquake itself. The earthquake did very little damage and caused very few casualties as far as we could tell. But the tsunami was just incredible. The magnitude 9 earthquake was one of the largest ever recorded. The tsunami was over 100 feet high in some places. You can see it coming in here. It's halfway up these trees, and at one point it actually overtops these trees. You can see it's destroyed the whole town, right? It's taking the whole town with it. This is what happens when the whole ocean comes in. Okay, this is in Japan over here on the western side of the Pacific. The tsunami, Japan had actually built seawalls to resist tsunamis, but they didn't build them high enough. You can see here the water's coming in, and it's like, oh yeah, this water is going over this thing here. This thing here is a 15-foot high seawall. Okay, so this water's coming in, it's dumping cars over a 15-foot high seawall like it's nothing. Okay, so the water was so high in some places. Look at this destruction. Okay, the whole town just wiped off the map except for one building, and this boat had to be carried all the way in and then just deposited by the water on top of this building, right? I mean, just incredible power from this water. Okay, well, a little more recently, this is a different part of the world. Now we're looking at the Eastern Pacifics, where this is South America here. So this is right offshore of the country of Chile, in northern Chile. 2014, there was a magnitude 8.2 earthquake. So magnitude 8.2 earthquake is actually larger than anything that can occur on the San Andreas Fault. And this just seems like commonplace for a place like Chile. But here we see, even in a country that has invested a lot of resources in earthquake resilience, extensive damage caused by the strong shaking. We see the tsunami from this wasn't huge, but it was enough to, ruin a lot of fishing boats in the port of Iquique, so nearby this earthquake. And actually, these earthquakes are still areas of really active study. I'm not going to go into any details here, but I work with a lot of colleagues using cutting edge seismic instruments and computers, and we determine what broke, where, when, why, how. And we publish these in paper, in journals right now. So we got this published in Nature 2014, one of the premier journals in the world studying this. And we followed up and we discovered that, in fact, there was a series of foreshocks that went bam, 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 and then triggered the big one. So it wasn't necessarily predictive, but it was, an indicator that there was something preceding this big earthquake. Okay, so these are areas of active research. 1 year later, as I said, Chile, these things happen all the time. Magnitude 8.3, just 1 year later, a little further to the south. Okay, again, extensive damage. This earthquake, both these earthquakes didn't cause many deaths, although a lot of damage because Chile is prepared for them. This one did have a bigger tsunami. You see this boat is not supposed to be sitting here on the sidewalk. This should have been in the water, but the tsunami carried it in and left it there. Again, I worked with lots of colleagues to study this in great detail. We investigated all sorts of things. What happened in the earthquake, its aftershocks, were things triggered. We saw these later aftershocks that happened elsewhere, a little further away. Some of them were quite large, mid-magnitude 7s. Some of these earthquakes weren't even on the boundary, on the fault. They were on other faults, totally other places. And these events end up being complicated. And so studying them is an area of really active research. So, kind of most recently, magnitude 7.8 in earthquake in Alaska back in July of 2020. That was already pretty big, right? Almost as big as anything we can get in California. That was followed this July by a magnitude 8.2 earthquake. Okay, giant earthquake right next door. Fortunately, the nearest town, the nearest populated town on Kodiak Island is about 300 miles away. So this earthquake did almost no damage, probably scared some, I don't even know what the wildlife is that lives up there, seals or something. But fortunately, not too damaging. So the question is, why can these, subduction zone earthquakes be so much bigger? Remember, we talked about the maximum earthquake width for the San Andreas, a vertical fault being about 10 to 15 miles. At that point, it gets down to this place where it's just too hot for earthquakes. Well, remember the geometry of subduction zones. These things are tilted. Okay, so because they're tilted, the maximum earthquake width on a subduction fault is much greater. It's like 100, 150 miles. Okay, so we have multiplied the size of the fault by 10 times, right? This is way, way bigger. It's not just like a little bigger, it's a lot bigger now. So this is like, this is a big deal. Okay, so this is, again, looking back at the Alaska earthquakes, 3 major events. I only mentioned 2 of them, but this orange one was really strange in here. And I just want to point out, again, these are areas of very active research. This orange one occurred in a region we didn't even think could have the standard subduction zone earthquakes, but it did. And we explained this and published it again in a high-end journal because these things are confusing. They don't always make sense, but we have to make sense of them if we're going to constrain the hazard. Okay, but we're going to take this earthquake because it's the recent big one, and we're going to compare this to California because we want to come back to California, right? Okay, so if we take this to California, that's how big the earthquake would have been, right? It's almost the size of the 1857 Fort Tejon earthquake in terms of its length, but it takes up like the entire San Joaquin Valley. This is a giant break in the earth, right? This is not some dinky little fault. This is a huge fundamental fracture in the earth. Okay, so this, fortunately, we do not have this here in Southern California. We are not at risk of this type of earthquake. Because this would be utterly devastating here if it ever did happen. Perhaps even more so than a giant earthquake on the San Andreas, which we saw could cause rivers to go the wrong way and every building to be knocked over. Okay, so just to knock this home, I want to compare earthquake sizes, compare the faults. So here's our local big event. This is the White Wolf earthquake from 1952, our Kern County earthquake. This is that Ridgecrest earthquake. Many of you may have felt this 2 years ago. It was a little bit smaller, so a little bit, you can see it's a little bit smaller there. The Fort Tejon earthquake broke the whole southern San Andreas. You can see it's much longer. But now I'm going to take these events and I'll put them in the corner so we can look at them compared to subduction earthquakes. And we see, the big subduction earthquakes, the 8s and 9s. These are really, really big faults that break. Here's the Alaska earthquake I just showed you, the green circle. Here's that Japan earthquake that caused the big tsunami. Look at this one down here. The Indonesia earthquake in 2004, which also caused a devastating tsunami, was almost 1,000 kilometers, 600 miles long. I mean, just a huge break in the earth. Okay, so just want to let you know that although here in Southern California, we don't have the worry of a subduction zone earthquake, there actually is a subduction zone up here, but you don't see any earthquakes here. This one's called Cascadia. Indeed, it is a subduction zone. We know this now, and we actually know it's had big earthquakes. We know because of the evidence of the tsunami that happened in 1700. So one piece of evidence are these trees that were killed by saltwater flooding from the ocean. The ocean came all the way in, sat there, killed all these trees, these ghost forests. There are native legends. The water suddenly receded, leaving the bay perfectly dry. It was 4 days reaching its lowest ebb, then it rose again without any waves or breakers till it had submerged the Cape. And in fact, the whole country except the tops of the mountains. Right? That's a big wave, right? This is not a little wave that comes in and, like a tide or something. This is a giant wave if it's submerging everything but mountains. We actually know this wave hit Japan. There's evidence of it hitting Japan. There was no earthquake, but the tsunami came in anyways across the entire Pacific Ocean. At midnight, a tsunami struck Kawasaki Village. Fires broke out and 20 houses were burned. In addition, 13 houses were reported destroyed by the tsunami. So obviously this is very devastating, but this provides us really important information. Not only do we know that this earthquake was destructive, we can use this information, even though we had no seismometers back then, we had no people writing down when this earthquake happened, Because the Japanese wrote down when the tsunami came in, we know when this earthquake happened to within about an hour, because we know how the tsunami goes across the Pacific Ocean. That's pretty good, right? For not having any modern seismic instrumentation. So we know it happened in 1700. Okay, so let me take you back to Southern California. What have we actually learned today? California is home to a lot of earthquakes, but even though some of them are big damaging events, they actually seem kind of puny when we compare them with earthquakes around the rest of the world. But the take-home message I want to give you is not necessarily to relax, actually quite the contrary. We've seen that in California, magnitude 6 to 7, maybe slightly larger earthquakes, they happen all over the place, not just in the places we expect them. And they can be quite damaging. So the reality is you don't need a giant earthquake that happens very rarely to cause damage. The moderate magnitude, 5, 6s, and 7s, if they happen under your house, they're going to do a lot of damage. And in California, those can happen all over the place. In fact, magnitude 6 earthquake right under you is way worse than a magnitude 8 hundreds of miles away, right? So the lesson is really to be prepared. You got to know what to do when an earthquake happens, and you got to be prepared ahead of time. So if an earthquake happens, we just remember, drop, cover, and hold on. Get under something sturdy like a table, and hold on, cover yourself, protect yourself. But also be prepared ahead of time. I tell people it's not the shaking that kills people, it's the things falling on you that kill people. So make sure things are secured. Tall furniture and water heaters and things like that. Make sure those are not going to fall on you. Make a plan with your family, right? If there's an earthquake and the power goes out or the phones go out, you need to be able to get in touch with them if these things happen. So as Tim mentioned at the beginning, you can find a lot more information about this at shakeout.org. It's really a great resource for being prepared for earthquakes, what to put in your earthquake kit and what kind of plan to make, how to secure things. So you should definitely check that out if you live anywhere near where earthquakes can happen. So that's all I got for you today. And I'm happy to take any of your questions. Thank you.
Okay. Thank you, Dr. Herman. I see only really one chat, and I'm going to repeat it. It's from Lucas Cotton. What was your favorite earthquake to study? This is from Luke to Dr. Herman.
Yeah, it's a great question. There's a special place in my heart for the first earthquake I ever studied. And that was about 10 years ago now. I studied a sequence of earthquakes in New Zealand. And that was really cool, not only because the earthquakes were strange, they were actually a lot like California in some ways. It was one of these earthquakes that was close to the major fault, but kind of off of it. It was a big earthquake under a populated city there, did a bunch of damage. The aftershock actually did more damage than the first big earthquake. So there was a lot of sort of confusing messaging, but also really interesting science about it. And that one really does hold a special place in my heart because it's when I learned to love this science. But I gotta say, the earthquake that happened this year in Alaska, the one that broke in a place we didn't expect it, that was weird and exciting, and that was really cool too. So old earthquakes and new earthquakes are all interesting.
We have a few more comments, one from Karen and Paul saying, thank you very much, Dr. Herman. Very informative.
You're welcome.
Ronald Walker says, how do you measure the 10x on the Richter scale?
Okay, I debated whether to talk about this in the class. Kind of feels like a class to me because this is how I teach as well. But I debated whether to talk about this in the Meet the Expert. The main thing I want to mention is we actually don't use the Richter scale anymore. And everybody in this talk, you can now take that home. If you ever hear somebody talking about the Richter scale, they don't know what they're talking about. We haven't used the Richter scale for over 50 years now. We have better ways of describing how big an earthquake is. We still use this magnitude, which is kind of what Charles Richter originally came up with, but it's now based, remember, on the actual size, the length of the earthquake, the width of the earthquake, how much the two sides moved past each other. So that measure is really more fundamental measurement than it is than the Richter scale, which was just a measure of how much the ground was shaking. So, remember, we had to we had to go all the way from CSUB campus to Southern California to go from a 4 to an 8, right? So 4 to an 8, it's not twice as big. It's many, many, many times bigger. It's a million times more energy released to go from a 4 to an 8. So an 8 releases a million times more energy than a 4. So it's actually not just factors of 10. It turns out the number is closer to about 32 for each magnitude unit. So if you go from a 4 to a 5 is 32 times bigger. If you go from a 4 to a 6, that's 1,000 times bigger. So you can see how that gets really big really fast. Good question.
All right. Some more thank yous from Ariana and Jennifer Cotton. So thank you. From Dan W. Hello from Denver, Dr. Herman. What are some of the necessary items that people usually forget to add to their earthquake kit?
Yeah, I mean, part of it is a little bit, I would say, dependent on you, right? It depends on what you need. If you take medications, you should probably put some extra medications in your earthquake kit. Maybe you should keep like a pair of shoes, right? If you're asleep and the earthquake happens and you just grab your bag and run outside, right? Do you wear shoes when you sleep? Probably not. So there's the standard stuff, things like a flashlight, water, food, all those things. But I think, you want to consider your situation. When you're asleep, what would you need for 24 hours or 3 days or something like that to get out, to make sure you just survive until you can find a more sort of stable location, no pun intended. But this is a really good question. And that's why I said go to shakeout.org, where they have tons and tons of resources and really checklists to go through. My job is more on the science side, so I study these scientifically, but they're really good sort of preparedness and risk communicators who have put that information at places like shakeout.org or the USGS or the Earthquake Center, things like that.
I'll just throw in, and you touched on this, Matt, is your communication systems that we're so used to, be it telephones, cell phones, television, internet, many of those may be down. And so if you have access to batteries and, to put in a radio or something, that's something I always think about anyway. That may not be the best thing, but make sure you have access to old style types of communication, I guess.
Yeah. Well, not only that, so California, we don't have to worry about this maybe quite as much, but there's some places I've been. Seattle's actually one of these, where if you're stuck in the wrong hill in Seattle, it could actually be really hard to leave that hill. And so you might not have power, you might not have water, you might not have phones, you might be stuck there. Bridges may have broken and things like that. So these are, again, it's all location dependent too. And in Bakersfield, we're all flat here, right? And so, you want to make sure you're safe. But then, you're not going to probably, at least in my house here, we're not going to be stuck in the house forever. We could just sort of, as long as we could get out, walk somewhere else. But again, this will just all be very dependent on where you are as well.
Some more thank yous. And then Karen and Paul say, when traveling in Alaska around Turnagain Arm, part of the town had sunk 10 to 15 feet as a result of the quake. Why does the land sink? Liquefaction. She's referring to the big 1964 Good Friday earthquake.
Yeah, this is a great question. So this is actually probably the area I am most active in research is what the ground does before, during, and after earthquakes and why it does that. So it turns out during an earthquake, and we can run computer models, physical models of how this works. During an earthquake, particularly these ones in places like Alaska, the part landward of the earthquake actually subsides. This was one of the major issues in Japan. Remember, I told you they built these seawalls up there. And in some places, the seawalls were almost high enough. They were like, I don't know, 2 or 3 feet higher than the wave. But it turns out during the earthquake, the ground moved down by about 4 feet in some places. So the ground moved down. That meant the wave could actually overtop the walls that were just barely barely tall enough. But this happens. This is a real thing. The ground actually does subside during these types of earthquakes. The ground doesn't actually move up or down too much in San Andreas style earthquakes, but in these earthquakes with faults that are tilted like that, that's a very, very common thing to see happen and has had really big effects. And actually is a way we can look at the historical record of earthquakes. We can actually go to places like the Pacific Northwest, and we can see in the geology, in the record on the coast, the ground going up and down. And how do we see this? This is actually really cool. I'm going to explain this because this is super cool. So it turns out that if you go into the water in the Pacific Northwest, there are these critters that live in there. And the critters that live in any certain part of the water depend on the water depth. If the water is really shallow, you get some critters. If the water is really deep, you get other critters. So if the ground surface goes up, the water effectively gets shallower. Different critters will live there. And vice versa. If the ground goes down, then we get the deeper water critters. And those critters die and they fall to the bottom and they get deposited and they pile up and they pile up and they pile up. So we can look at the layers of different critters and we can tell what the ground level was. So we can go back thousands of years to see the coast in Oregon, in Washington, in Northern California going up and down. And it does it sort of slowly, 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 slowly. Then boom, there's an earthquake. Slowly, 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 and boom, there's an earthquake. So in fact, this is a real thing that happens, and we can use it geologically to figure out where and how big earthquakes were in the past. So great question.
Okay, another thank you from Jaslyn Woolfolk pointing out the importance of an earthquake kit. And again, Karen and Paul, thank you. We're coming up on our time commitment here, but thank you very much. Anyone, if you have another question, stick it in there. I wanted to throw in, Matt, is there anything new with the Universal California earthquake rupture forecast? Some folks may be familiar with that. I know the USURF 3 came out in 2015. But it's basically the forecast for where earthquakes are going to occur, or what the risk is of earthquakes, not only on the San Andreas Fault, but throughout California along USURF. Do you have any comments about that, or there's so many things we can talk about.
There's a lot of people in California who have worked very hard on USURF. So this is sort of a probabilistic estimate of what areas are going to shake, how hard, and over what time frame. I think this is really useful for engineers, and it's really useful for insurance companies. From the perspective of scientists, it works until it doesn't. And that has a couple of, okay, what do I mean by that? Well, this magnitude 7.1 earthquake here, the Ridgecrest earthquake 2 years ago, that was not highlighted as an area in USURF that's like, yes, this is a particular fault that we should be worried about. The reality is these things are not predictable. Okay, you could call them chaotic, but that's not really a useful thing either. they interact with each other. Even any one specific fault can have earthquakes at irregular intervals. I mean, it just is not predictable. And so the forecasts have some utility until they don't. The other issue with that is that the forecasts just use what we already know about how faults work, about how earthquakes work. That's great, but that's not what I work on. I work on how faults work, how earthquakes work. And so if I just sit and say, yes, we've got a probabilistic estimate, I'm out of a job. So, it really is important to me to figure out how these work. Now, hopefully what I do can then be put in to one of these probabilistic models to say, yes, we should need to think about maybe fault interaction a little bit more, how these earthquakes can go pop, 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 and then a big one. Or maybe we need to think about places like Ridgecrest. Where are the unmapped faults that could have an earthquake? How often do those have earthquakes? If we have an earthquake in Ridgecrest, does it change when we're going to have an earthquake on this feature here, which this crosses Ridgecrest, this Garlock fault? I mean, there's all these questions here about interactions, and that's really where my research is focused on. And hopefully down the road in a decade or 2 decades, that can be plugged into a probabilistic map of hazards in California.
Last question here from Ronald. Last movement on the Garlock Fault.
Oh man, I think you might have stumped me. I was looking at this when I was studying the Ridgecrest earthquake, and I can't remember the date off the top of my head. Now, I could use a sort of flippant answer, and you can see earthquakes on the Garlock Fault in this image. So we know there's been earthquakes, there's been seismicity. The Garlock Fault has moved since 1990. These earthquakes are since 1990. But the last big earthquake on the Garlock Fault, it is not as regular as the San Andreas. I know that. So it's not every 150, 250 years or something. It's less frequent. But I can't remember off the top of my head if it was 500 years ago or 1,000 years ago or what. But what I do remember is that the Garlock Fault, some faults, they don't always go off in the same time interval. It might be 150 years, might be 450 years. But the Garlock Fault is particularly irregular. There are time periods where it just doesn't have earthquakes for thousands of years, and then other time periods where it has earthquakes every century or two. So it is an unusual fault in that sense. And why it's there, I think I saw Chris come in here. We need to think about that a little bit.
Okay, and we just got, let's see, from Ariana.
Yeah.
Most recently notable event on Garlock was 5.7 near Mojave on July 11th, 1992. Is thought to have been triggered by the Landers earthquake.
Yeah, I mean, that may be true. Landers is a little far away in my mind to have triggered that, but I mean, it's possible, I guess. I haven't, as I said, I haven't explored it in great detail, but that is a possibility for sure.
I know the Garlock is one of those that historically they've separated into a western, eastern, and central segments, and the frequency is all over the place, but it's different for each segment.
Yeah,
I read.
Yeah. Google is a great first step into understanding it, but it's only the first step. So that information is very useful. But 2019 was interesting. It did have some small earthquakes, but actually the Garlock Fault after Ridgecrest, right down here, so just south of here where there aren't many earthquakes, it moved, but it actually moved without having any earthquakes. It just sort of like, the two sides of the fault were like Teflon between them, or like they were lubricated. So they actually kind of slid past each other without any earthquakes. We can see this with satellites really clearly. And so, we call that aseismic, right? It's motion on a fault without seismicity. So, that's another thing we've got to add to this, because, how many of these faults are aseismic or partially aseismic? We know parts of the San Andreas up to the northwest here are aseismic, and that throws a wrench in everything too. So this brings up some really important issues.
You know, we could do this forever and a day, and it would be very interesting. There's so many aspects to earthquake preparedness, understanding the historical aspects of earthquakes, the geophysics, the seismology, the understanding of the Earth's crust. Maybe perhaps we can have you back again, Dr. Herman, for addressing some of these things.
I would be
But
happy to, yeah.
Yeah, I think we'll close it here with a few words, if that's all right, unless Dr. Herman, you have anything.
No, I'm all finished. Thank you.
So thanks to everyone for attending today, and thanks to Dr. Herman for his time in preparing this presentation and sharing his knowledge with us. The museum would love to have you back again soon, Dr. Herman. Before we go, I want to mention that if you enjoyed today's event, I did, please consider making a donation to buenavistamuseum.org/donate. Your generosity is what makes events like this possible. So thanks to everyone for coming, and keep an eye on our website for other Meet the Expert events like this one. So once again, thanks everyone, and good night.
Thank you all for coming.